Hello, welcome to the second part of the video on periodic table and periodicity, which is a part of the syllabus for the first semester chemistry under inorganic section. So, in this video, we'll be learning what is electron gain enthalpy, what is successive electron gain enthalpy, and a variation of the electron gain enthalpy across a period and in a group, and the explanation for the observed trend. So in the earlier video, we have defined what is an ionization enthalpy, which is an amount of the energy required to remove an electron from a neutral gaseous atom, and the successive ionization enthalpy, and the various factors such as atomic size, effective nuclear charge, electronic configuration, screening effect, which affects the ionization enthalpy. Apart from that, we have also learned the application of ionization enthalpy, which gives an idea about the reactivity, the reducing power, and it will also tell about the number of electrons in the outer shell and whether an element is a metal or a non-metal. Similarly, we have also made an understanding that is the variation of ionization enthalpy around a group and in a period. In a group, it decreases and in a period, it increases. Now coming to the electron gain enthalpy. So just as the ionization energy measures the tendency of an atom to change into a cation, the electron gain enthalpy is also called as electron affinity. It is a measure of the tendency of an atom to change into an anion. So it is defined as the amount of the energy which is released when an electron is added to an isolated gaseous neutral atom. So it measures the tendency of an atom to become an anion. Like we have represented the ionization enthalpy, the electron gain enthalpy can also be represented by the following equation. A neutral gaseous atom, here we are adding an electron and the amount of the energy which is involved during the process, we call it by the name electron gain enthalpy, and it is usually expressed in kilojoules per mole or electron volts per atom. Coming to the electron gain enthalpy, it gives a measure of the tightness to which the additional electron is held by the nucleus of an atom. The greater the energy is released in the process of taking up the extra electron, the greater is the electron gain enthalpy. So let us learn in detail the electron gain enthalpy. So when an electron is added to a neutral gaseous atom to convert into a negative ion, the enthalpy changes which is accompanied during this process is defined as electron gain enthalpy or the electron affinity. So the electron gain enthalpy provides a measure of the ease with which to an atom you can add up an electron to form an anion, and it is represented by the following equation. Neutral gaseous atom taking up an electron get converted to an anion, and the amount of the energy that is involved during this process, we call it by the name electron gain enthalpy. Electron and affinity or the electron gain enthalpy can be both an exothermic or an endothermic depending on the element. So, on the basis of the nature of the element, the process of accepting the electron in an atom can be both exothermic and endothermic. In general, The energy is released when an electron is added to an atom, and the electron gain enthalpy for such elements is negative. The electron gain enthalpy of halogen is very highly negative because it needs only one electron to achieve the nearest noble gas configuration, and the same is also true with the noble gases, which is highly positive here because the extra electron has to be placed in the next higher principal quantum number, which will require lots of energy. So the electron gain enthalpy depending on the element, the process of adding an electron to an atom can be either an endothermic or exothermic, and for many elements the energy that is released when the electron is added to the atom and the electron gain enthalpy is negative. So this is the figure or the diagram which gives about the electron affinity of the various elements belonging to the periodic table. So as discussed, the halogens, when we look at the electron affinity, they have very high electron affinity because of the tendency to take up an electron and gain the octet configuration. So the electron gain enthalpy is almost zero in the case of the noble gases because here the electron has to be added to the next energy level sub-level. So coming to the various factors which affect the electron gain enthalpy, this is the effective nuclear charge, atomic size, and the electronic configuration. So, coming to the effective nuclear charge, with increase in effective nuclear charge, the force of attraction exerted by the nucleus on the electron increases. Consequently, the atom has a greater tendency to attract additional electron, that is, the electron gain enthalpy increases, which that is, it becomes more negative. Coming to the second factor, that is the atomic size. With decrease in the size, effective nuclear charge increases and hence electron gain enthalpy increases. And coming to the very important, that is the electronic configuration is also a very key factor which affects the electron gain enthalpy. The value of electron gain enthalpy depends effectively on the electronic configuration of elements. For example, the elements with stable electronic configuration possess lower or less negative value of electron gain enthalpy. For example, when we take the noble gases, they have almost practically zero or positive electron gain enthalpy. So this is the noble gases helium, neon, argon, krypton and xenon. And when we look the electron gain enthalpy, it is almost zero. Here the reason because is they have the tendency to or they have no tendency to gain an additional electron as they have already the stable Ns2 Np6 configuration. So when we look up the other halogens, they have high electron affinity or electron gain enthalpy, that is fluorine minus 328, Cl minus 349, bromine minus 325 and iodine minus 295. So they have high electron affinity. This is due to the strong tendency to gain an additional electron and to change into stable Ns2 Np6 configuration. And coming to the successive electron gain enthalpy, like we have the second and the third ionization energy, we can also have second and third electron gain enthalpy. So the energy that is released when an electron is added to an isolated gaseous atom is the first electron gain enthalpy. So this we have discussed earlier. Similarly, there can be a second and higher electron gain enthalpies. So when a first electron is added to an atom, it becomes a negatively charged. And to this negatively charged, when we are going to add up the second electron, it is the second electron gain enthalpy. So after the addition of one electron, the atom becomes negatively charged. So the addition of second electron is opposed by the Coulombic forces of repulsion and the energy has to be supplied for its addition. The successive electron gain enthalpy becomes endothermic. So this can be illustrated by taking the element sulfur. So when the sulfur, when we add a first electron, it gets converted into an ion and the electron gain enthalpy is minus 200 kilojoules per mole. And when we add the second electron to the first anion, the electron gain enthalpy is plus 590 kilojoules. So if an atom has a spontaneous tendency, that is a positive tendency to gain an electron, that is the first electron gain enthalpy. The second, it is reluctant to accept the second electron. So to this anion, when we are going to add the second electron, there will be a stronger repulsion and hence the second electron gain enthalpy will be higher or the energy has to be supplied in the case of second. So in detail, the successive electron gain enthalpy when an atom accepts the electron one after the other and not simultaneously, the energy involved are known as successive electron gain enthalpy. However, the addition of second and third electron may be negative but mostly positive because uninegative ion which is formed during the first addition experience a repulsive force from the electronic cloud of the anion. So, when an atom has a spontaneous tendency, that is the positive tendency to gain an electron, then conventionally the electron affinity is said to be positive. And if an atom is reluctant to gain an electron, that it has a negative tendency to gain an electron and it is forced to accept the electron. The electron affinity we call it to be the negative. Thus, in the case of oxygen, the first electron affinity or electron gain enthalpy is positive around minus 141 kilojoules per mole. But however, the anion of oxygen, when we are going to add up the second electron, the electron gain enthalpy is plus 780 kilojoules. So, in other words, oxygen atom has a positive tendency to accept an electron. However, the second electron affinity is negative of 780 kilojoules because the energy has to be supplied to convert 1 mole of anion to the divalent anion. And this is all about the successive electron gain enthalpy. Coming to the variation of electron gain enthalpy in the periodic table. In general, when we take the variation of electron gain enthalpy, it decreases across down the group and it increases along the period. So when we look along the period, the electron gain enthalpy increases from left to right. So as we move from left to right along the period, the atomic size decreases and hence the force of attraction exerted by the nucleus on the electron increases. Consequently, the atom has a greater tendency to attract additional electron and hence the electron gain enthalpy increases along the period. Now coming to the down the group, the electron gain enthalpy decreases. So all moving down the group, that is, as we move down the group, the atomic size increases and the effective nuclear charge also increases. But the net effect here, the atomic size is more prominent than the nuclear charge and hence the effective nuclear attraction for the electron decreases. Consequently, the atom has a lesser tendency to attract the additional electron and hence electron gain enthalpy decreases. Coming to the few abnormalities or the variation of the first electron affinity. So these are the halogen group. Among your halogens, we have fluorine, chlorine, bromine, iodine, acetylene. On this side, we have the electron affinity in kilojoules per moles. So when we look at the electron affinities of the halogens, they have very high electron affinity, and the reason here is they have a strong tendency to gain an additional electron and acquire the stable Ns2 Np6 configuration or the octet configuration. So when we compare the electron gain enthalpy among the halogens, that is from chlorine to iodine, that is on moving down the group as discussed earlier, the electron affinity or the electron gain decreases down the group, that is from chlorine to iodine. But when we look at the fluorine, it has the electron affinity is unexpectedly low when compared to the chlorine. It is probably due to the small size of the atom. The addition of an extra electron produces a high electron charge density in a relatively compared to p subshell, resulting in a strong electron-electron repulsion. And this repulsive forces between the electron imply the low electron affinity. Apart from the size of the atom discussed above, the electronic configuration of the elements also influences the first electron affinity considerably. When we take the noble gases or the inert elements, helium, neon, argon, krypton, xenon, radon, and they have a stable Ns2 Np6 configuration. And when we look at the electron affinities or electron gain enthalpy of noble gases, it is almost zero because of the stable Ns2 Np6 configuration in their valency shell, and there is no chances for the addition of an electron, that is the extra electron. Similarly, when we look the electronic affinities of beryllium, magnesium, nitrogen, also they also have very low electron affinity or practically it is almost zero. So when we look the electronic configuration of beryllium and magnesium, beryllium has the 2s2, 3s2 and 4s2 in the case of calcium, and here they have completely filled a subshell, so they have a little tendency to take up an electron electron, and hence the electron gain enthalpy is almost zero. When we take the nitrogen, its electronic configuration is 2s2 and P3 to P3. So it is completely filled s subshell and half filled p orbital, and hence it has a less affinity to take up the an electron, and hence it's almost a very low electron affinity. The electron affinity of the beryllium is less to that of lithium. Once again, although the atomic size of beryllium is less than that of lithium, and similarly is also the story with the case of nitrogen and oxygen. The electron affinity of nitrogen is less than that of oxygen, although the atomic size of oxygen is less than that of nitrogen, and hence the atomic size is not the only criteria in determining the electron affinity. And coming to the summary of this video, we have defined what is an electron gain enthalpy. It is a tendency of an atom to change into an anion, or it is the amount of the energy which is released when an electron is added to a gaseous isolated atom or ion, and the successive electron gain enthalpy is the addition of an extra electron to the first anion, and we have learned in detail. Coming to the variation of electron gain enthalpy in a period and a group, we have looked electron affinity in a group down decreases, whereas it increases across the period. And these are the references for this video. Thank you.